Good evening, sir. My name is Ronak. I'm a third year engineering physics student, and my project, CWS project, is on prediction of Lorenz attractor trajectories using LSTM networks. So, yeah, getting started. What is the Lorenz system? The Lorenz system is a set of three coupled nonlinear differential equations, which were developed by Edward Lorenz in 1963 to model atmospheric convection. It is one of the most famous examples of chaotic dynamical systems. So going forward, why do we need to study it and what are its applications? So yeah, as I had mentioned that Lorentz system is dynamical in nature. So it has a very chaotic behavior, which is that with very minute changes in its initial conditions, it can have very different outcomes. It can have very different outcomes. So yeah, with very small changes in its initial conditions, the outputs can vary vastly. So yeah, this effect is or property is also known as the butterfly effect, which is that if a butterfly flaps its wings, say in Roorkee, there will be a sandstorm in the deserts of Las Vegas, Nevada, or anything or any other place like Sahara, etc. So yeah, this marked the beginning of chaos theory, showing that long-term prediction is fundamentally limited in many natural systems such as weather and fluid motion. Despite its simplicity, the Lorentz system captures the essence of complex, non-linear, and realistic behaviors, making it a cornerstone model for understanding chaotic dynamics. One of the applications that is there is the weather and climate modeling. Tiny measurement errors in temperature or pressure can quickly amplify, making long-term forecasts unreliable. Modern weather models uses Lorenz's chaos theory to improve short-term predictions and define the limits of predictability. The other application is plasma physics and fusion research. In Tokamak's instrument, nonlinear plasma and magnetic field interaction cause instabilities and turbulence. Lorentz type models help describe these chaotic transitions, aiding in stable fusion control and studying magnetic reconnection and energy transfer. The other application is in coronal mass ejection, that is, and space weather. The coronal mass ejection, massive solar plasma bursts exhibit chaotic behavior. So Lorentz-like models can help in, predicting its nature and, analyzing and studying how that works and why these effects are, seen. Talking about the Lorentz equations, these are the Lorentz equations that I had used in my project, and these are the parameters that I have used 10, 20, 10, 8 by 3 respectively, for sigma, rho, and beta. Okay, coming to the Lorentz attractor. Lorentz attractor is the name given to the beautiful butterfly-like shape of the whole system. So yeah, I'm going to talk about this shape now. Initially, when the value of rho is less than 1, the system is quite stable and it has a global stable at the origin. But as the value of rho is increased from 1 greater than 1 till the point of rho c, that is 24.74, there are non-trivial fixed points which become the stable foci for the whole system. But these equilibrium lose its stability through a Hopf bifurcation, leading to the onset of chaotic motion that we observe, we had observed in the previous, that I had mentioned earlier. So yeah, that I mentioned over here. So yeah, leading to the onset of chaotic motion. So the trajectory that we see over here, that does not converge to a point or a periodic orbit, but it instead evolves into a strange attractor to a Lorentz attractor that I had mentioned. So it has a few characteristics in itself, that is boundness. The trajectory remains confined to a finite region of phase space. The second one is periodicity. The motion never repeats. And the third one is fractality. The attractor has non-integer Hausdorff dimension. That is the fractal constant. That is 2.06. That is the attractor's shape is between a surface and a volume, but it is very much closer to a surface as it is only 0.26 from the surface dimension, that is 2. So yeah, again the sensitivity to initial conditions, that is as it is a chaotic non-dynamical system, it is very sensitive to initial conditions. and the constant here is 0.905, the Lyapunov exponent constant. Talking about the technical part of what I have done in this project, it's a data. Firstly, I generated data. I did not use any other data set, to implement the ML models, etc. The first thing I did was data generation for the Lorenz system. I use Python's SciPy library solve function to with parameters 10, 20, and 100 to numerically integrate the Lorentz equations. After that, the whole trajectory was simulated for 50 seconds with 0.01 time steps. Yeah, giving me about 5k points for each variable x, y, z. To improve the generalization, multiple trajectories. I generated multiple trajectories with different initial conditions between the -20 to 20 for all three x, y, and z. So all the trajectories eventually form the characteristic Lorenz attractor butterfly-like shape. The resulting data was then normalized in the standard scalar using the standard scalar function and split into overlapping sequences of 50 inputs, which then gave me 10 outputs. So yeah, there's a snippet of the code I had used over here. Yeah, talking about the divergence of Lorentz system, as it is a chaotic in behavior, as it is a chaotic behavior, the system diverges very easily, and I have plotted those divergences over here for two different initial conditions, which vary by a very small unit. So yeah, these have a very huge divergent features. Yeah, and this is the distance between the trajectories on the log scale with time. So what I'm going to do in this project is I'm going to use LSTM network to predict the future values of the Lorenz attractor, as it can be very computationally expensive to do that using numerically. So yeah, what I've done is I've implemented it for short-term predictions, but this can be, implemented for long-term predictions too, which I tried to do, but which did not work quite well for me. So which will be seen in the results upcoming results. So yeah, talking about how I implemented this. Firstly, I used a two-stacked LSTM layer with 120 DNet units with inputs of 50 time steps of XYZ coordinates. The outputs were 10 future steps predicted for all the three variables. A fully connected layer maps the final hidden state to the output. The rectified linear unit activation adds the non-linearity, helping the model learn the chaotic dynamics of the Lorentz attractor. So yeah, here the snippet of the code I had used. Yeah, to improve the efficiency of the predicted values, I use loss function mean squared error, which minimizes the differences between predicted and the true trajectory. With that, I have also used optimizer and scheduler. With optimizer that I've used is Adam optimizer with a learning rate of 0.001. The batch size was 128 samples per batch, and the number of epochs I had trained was 120 epochs for stable convergence. Yeah, for long-term forecasting, as I mentioned, I use auto-regressive approach, even though this is not a very good approach, but yeah, this was in my knowledge, so I had used this only. So yeah, in this, I predicted the next 10 steps, which were then fed back as the input for the next round. This iterative method extends prediction up to 1k steps, letting the LSTM generate full Lorentz trajectories. So yeah, here are the results that I was talking about. Till the point of 500 to 600 steps, the predicted values quite in hand with the true values. But as it crosses 500, the predicted values go very differently. It diverges very differently from the true values, as you can see for all the three of X, Y, and Z. But still, it still maintains the non-dynamical system nature of the Lorenz attractor, So yeah, the model did learn the non-dynamical system, but it could not quite replicate exactly the uh, nature of the Lorenz attractor. So yeah, it can be also seen over here, where initially the where initially it was very close to the true values, but then it started diverging and everything, diverging, and then it just went off. These can be seen in all the X, Y, and Z values. So yeah. Talking about the error growth over rate, initially the error growth was 0 till 400, then it started increase a bit. and then it went on increasing, and then again dropped down. So yeah, okay. Talking about the value of R square, the R square's value is zero point 0.4. It is quite less because of the errors that were found in this region, that is post 700 and 750. Because of these errors, the errors between around 800. This is the reason that the R square value has dropped to zero point 0.4. But for the values between 0 and 600 or 500, the R square value was quite low and about 0.98 to be precise. So yeah, concluding the whole project for the first 5 to 600 steps, 0.98 was the R square value, and the predicted XYZ were very closely to the matched true trajectory, demonstrating that the model worked effectively for short-term predictions of the Lorenz system. After 600 steps, the prediction began to diverge due to the chaotic nature of the system, where small errors grew exponentially. Despite this, as I had also mentioned earlier, the LSTM maintained the non-dynamical and the chaotic nature of the Lorenz system, and it did behave like a Lorenz attractor, but just with different initial conditions. So yeah, that is what I had mentioned. I could not replicate it for longer time steps, but I will be working on that in future. I believe, yeah. In summary, the model platform performs well for short-term forecasting and successfully replicates chaotic behavior. But for long term, it only replicates the chaotic behavior, but it did not go quite along with the values of true values of the Lorenz attack. So yeah, future scope and improvements. Talking about this, the future scope can be that this same approach can be applied in weather forecasting. That is there. It is being applied in weather forecasting actually. But what I've thought was that it could be applied in financial data modeling. Predicting a stock of some random a small company which can be affected due to buying and selling of some other stock. So yeah, the some techniques that can be used to improve teacher forcing, scheduled sampling, or sequence to sequence architecture, etc. So yeah, this was my project. Thank you.